Hello everyone. This tutorial is to get you started with Virtuoso and Eldo. Uh, so we will be starting with the schematic of CMOS inverter, perform Eldo as well as ADL simulations, and then we will be finally moving on to the layout of CMOS inverter. So before you begin, you need to execute all these commands uh, uh, one by one on your terminal to set the corresponding files on the server. So after you are done with this step, you will see a CMOS 65 directory on your desktop. You need to move inside this directory. So you see now I am inside the CMOS 65 directory, and we will always be invoking the Virtuoso from inside this folder. So firstly, we need to uh, convert this bash cell to the C cell, and then we will be sourcing the CSHRC file, which contains path to invoke different tools. Once we are done with this, to invoke Virtuoso, we only need to type Virtuoso, and so there are two things. You can invoke Virtuoso only by typing Virtuoso, or you can invoke it in the background mode by pressing ampersand after Virtuoso. So I am opening it in the background mode. So once you press enter, you will see a log window on the screen. So whatever you do on the Virtuoso, whether it's about schematic or performing ADL simulations, or uh, about different things in the layout, everything will be popped as messages in this log window. So to begin with the schematic on Virtuoso, we need to create the library where we will be creating different cells. So for that, you go to File, you go to New, and you create your own library. So you can name this library as anything what you want. I am naming it as lab, and then we need to attach it to the existing technology library. So this existing technology library will have certain instances of the cells that you will be using it to create circuits in your library. So I'll be attaching it to the existing technology library CMOS 065. So CMOS 065 is a existing technology library which has got the channel length of 65 nanometer. So after this, you press on apply and then press on OK. So once you do this step, you will see that in the log window, the message appears that design library lab has been successfully attached to the technology library. And now you can move to create different cells in the library. So for that, you need to go on File, New, followed by Cell View, and then from here you need to select the library that you have created. We have created lab, and then you need to name the cell whatever you want to create. Since we are drawing the schematic of CMOS inverter, I'll be naming it as INV. Then select for now on we will be keeping the view as schematic only. So and then we will be opening the schematic L only, and then you need to click on OK. So you need to click on session. So you'll see that schematic editor of Virtuoso has been opened, and now you can create the schematic circuit of CMOS inverter here. So to to get the instance for NMOS and PMOSes, we need to click here, create instance. Or what you can do is the keyboard shortcut to create instance is I. So you can click I button on the keyboard, and that will again open uh, this option. And then you need to go to browse, and then you need to, here in the library menu, you need to select the existing technology library that you have associated with your library. Inside the CMOS 065, there are various cells like for PMOS, we have PSVT-LP. So P stands for PMOS, SVT stands for standard threshold voltage, and LP stands for low power. Similarly, you will see that there is NLVT-LP or PLVT-LP. So this is for low threshold voltage and low power. So To start with, uh, we will be taking the instance of PSVTLP, and then click on symbol and then click on close. So you'll see that different by default a particular width and length of a PMOS is present. Uh, you can click on hide option here. So so you will see that PMOS will keep on hovering with your mouse button unless you click on the screen. So click where you want to place the PMOS. And then to get rid of this PMOS instance, you need to press escape button on the keyboard. So now you see that the PMOS has been placed. Now to similarly, we will be creating an instance of NMOS. So again, click on I, go to browse, and here inside the CMOS 065, you need to search for NSVTLP. NMOS of standard threshold voltage and low power. And then if you want to change the width and length of NMOS, you can do it from here. For now on, I am keeping the length as it is. So now you will see the NMOS is hovering with your mouse. You can click it if you want to, wherever you want to place the NMOS. So now suppose you have placed the PMOS and NMOSes, and you want to know what instance it is. So you can click on this uh, uh, instance and then press Q button on the keyboard. So Q stands for properties. The properties window for that particular instance will open, and here you can see the width and length, or you can also change the width and length from here on. So this is about looking at the properties of various instance. Other thing is, at any point of time, to change the width and length, you just need to select the particular instance, and here you will see the option to change the particular width and length here if you have missed or forgotten to change the width and length of PMOS and NMOS at the initial stage. Another thing is, if you want to rotate a particular instance, you can do it by here you have the option to rotate right, left, flip horizontal or vertical. So suppose I want to rotate right, I just need to select the rotate right option and then press it on the instance. So you will see the NMOS has been rotated. Similarly, we can rotate anywhere we want. The keyboard shortcut for rotate option is R. Um, Another thing is, if you want to do undo, the you can do undo by pressing U button on the keyboard. U is the keyboard shortcut for undo. So you see the instance has been the rotated instance has been undone. Uh, so after you place these instances and you look into the properties of instance, we need to connect uh, it with the with wires, so that we are able to achieve the schematic of CMOS inverter. So for that, you need to create narrow wire. Either you need to go to create narrow wire, or what you can do is you can press W on the keyboard. So W is the keyboard shortcut to create the narrow wire. So to make our CMOS inverter, we need to connect the drain of both PMOS and NMOSes, as well as gate of both PMOS and NMOSes. And to get rid of body effect, we need to connect the body with the source of corresponding transistors. So you can see that I have made the corresponding connections. And now we need to create the pin. So for to create the pin, either you go here on the create pin option, or the keyboard shortcut to create pin is P. So we need to create two input pins, that is in and VDD. So I'll be making two pins. Once you do this, you'll see that the pin will be hovering with your mouse, and you can press wherever you want to place those pins. Again, you need to create the input output pin for the ground. So in the direction, you need to select input output, and then uh, you need to place this ground pin. And finally, you also need to create a output pin. So I'll be naming it as out, and then the direction I'll be naming it, giving it as output, and I'll be placing it here. So now I'll be making the connections from the instances to the pin. So for that, we need to either create wire or press W on the keyboard to create the wire. And then I need to make the corresponding connections from the pin. So after I make these connections, uh, you will see that the CMOS inverter that we wanted to make, the schematic of CMOS inverter has been made. You can press on this check and save option, and if no warning appears, it means the schematic you have made is correct. Suppose I delete this wire and then try to check and save, you will see there are three warnings. So if you will go and see that since these three things aren't connected, the tool is giving me a highlighted cross symbol here, uh, highlighting that I have done some mistakes. So I need to connect it with wire by pressing W and creating a wire there. And now if I check and save, you see that there is no warning, and we are done with the schematic of CMOS inverter. Next, to perform the simulation on ADEL, you need to go to launch and then ADEL, and then you need to click on session. So keep on clicking session. So that finally you are inside this ADEL. Uh, to start with, we need to click on analysis and choose analysis to choose what type of analysis we want to perform. So there are various options. As you can see that we can perform transient, DC, AC, and different types of analysis. For now on, we will be performing the transient analysis. So, and then we need to select the stop time, that till what time our simulation is going to run. So let's select, uh, let's put the number as 100 nanoseconds, so that the simulation is going to run for 100 nanoseconds. And then you need to click on enabled and then press on apply and OK. So you see that a transient simulation option will start showing up on the ADL. And so to begin with, you need to give stimuli. So we need to give the stimuli for different pins we have created. Like for the ground, to give every stimuli, you need to first for select that particular input stimuli. So we have ground is already selected, you need to enable it, and then we need to give the DC signal at the ground, and the value of DC signal is going to be 0 volt. So we apply the corresponding ground, then we move to VDD, click on enabled, change the function as DC, and the VDD voltage I will be setting as 1.08. You can set it whatever you want. Then click on apply, and then at the input, since we are interested in performing the transient simulation and inspect the input output behavior of the CMOS inverter, I'll be giving the pulse signal at input. So let me do a change the function to pulse, and then the voltage level, one is the low voltage level, which I'll be giving it as 0, and the high voltage level I'll be giving it as 1.08 volt. And since we are going to give the pulse waveform at input, we need to also give the period of this pulse waveform. So for now on, let's create the give the period as 10 nanosecond, and then you to get the different duty cycle, uh, you need to also give the pulse width. So for now on, I'll be making the pulse with duty cycle of 50%. So I am not giving the duty cycle in case pulse width. In case you want to uh, get a different duty cycle number, you need to give the pulse width as duration of the input pulse for which your pulse is going to be 1. And then you need to click on apply, and then you need to click on OK. So after setting up the stimuli, you can change the temperature from here. I am keeping it as 27 from now on. You need to also give the corner files. For that you need to go to this model library option and then click here. So you need to click here, and then uh, you need to go on the corners. So there are different corners like typical, slow, fast, slow, fast, slow, and fast. And these corners are used to model the process variations on our die. So for now on, you can select any process corner, whatever you want, whatever is required for the particular simulation. Uh, to start with, I'm just choosing typical, press on apply, click on apply, and then OK. So till now, we have chosen the our analysis, given the stimuli, and then chosen our corner file. Then we need to plot the output. For that, you need to go to output, and then to be plotted, and then click on select on design. And then you need to select whatever points you want to plot on the graph. So I want to plot input and output for now on. So I'll be pressing on input as well as output. And then you need to finally do this netlist and run option to run the particular simulation. So after you are done with this step, you will see the simulation log window here, which will have uh, different parameter values, and based on these parameter values the corresponding graph has been plotted. You need to press here split all strips to uh, distinguish between input and output, and so you will see that when the input is high the output is low, and when the input is low the output is high. So this is the nature of our CMOS inverter that you have created. So you can zoom over this graph, and you'll see there is a small bump over here. Uh, Once the output starts to discharge, there is a small bump before which it starts discharging, and this is basically due to capacitive coupling there. So this was all about the plotting input and output on ADEL. So moving forward, to perform the simulations on Mentor Graphics Eldo, we need to extract the gate level netlist from Cadence Virtuoso, and then we will be using the CIR file to simulate the gate level netlist. So for that, we first need to go into this log window, go to the file option, and then export CDL. And here in the library option, you need to select this library, which is lab you have created, and select the schematic that you have created. Further, you have to name this output CDL file as inverter.src.net. So uh, after doing these things, you have to click on apply and then click on OK. So you'll see that inverter.src.netlist has been generated. So what you need to do is you need to go into the CMOS 65 directory. So, and here you will see that inverter.source.net file has been created. You can copy this file and then move on to the desktop and paste it inside the Eldo folder. And here you need to create this another folder, and you can name it as INV. And here you need to paste the source netlist file along with the CIR file that you need to write. So I have already written the CIR file. Let me open both the files. So inside the netlist, the changes that you need to make is you need to change this instantiation name from MM0 to something else. Similarly, you need to do for all the transistors. So since we have only two transistors, we need to change this MM0 to something else. So let me change it to MM1 and XM1. The reason being, in the model files where we have the transistors, there also the name of the transistors are instantiated with MM0 and MM1. And so due to the duplication error, the tool will flag me an error if I don't change the name of instantiation here. Further, moving on to the CIR file, you can see that just like we we gave different PVT values using the corner files, and we gave different stimulus and all, and plotted the values in ADEL. We need to do the same in this CIR file. So you can see that all the statements that are beginning with this star option are all comments in this CIR file. Other than that, the first step is to include the gate level netlist. So I am using dot include and then the name of the netlist file to include that particular netlist. Uh, and then we need to define the PVT values. So for process, you need to include the model file corresponding to the particular process corner. So you can see that I am including min and minp.cir. It signifies that the process corner that we are using is slow. For fast, you need to just include max and maxp.cir file. And for typical, you need to include typn and typ peak.cir, and similarly for all the different process corners. You need to specify the voltage and temperature values by defining it as a parameter using .param, and then we name it as supply. So we take three different parameters: supply, T end, and temperature, and uh, give it the value accordingly. Uh, Other than that, you can see that we are specifying a capacitor which is connected between output and ground, and the value of capacitor is taken to be 20 femtofarad. So this is how we specify the load at the output. So after we have given the PVT values, we also need to give the stimulus. So for stimulus, we need to give three different input signals as we have given in ADL. For VDD, uh, we need to give it the value equal to the supply. So positive voltage of VDD has to be equal to supply, which is 1.08 volt. The ground we are giving as 0. And for the input, since we want to see the input output waveforms, we want to give input as a pulse. So the for the pulse, we need to use this function pulse, and then this 0 signifies that the lower level of the pulse is at 0 volt, the upper level will be at 1.08 volt. Next, this 0 signifies the starting delay. So since we are not giving any delay to the pulse, we are taking it as 0. And then this 0 picosecond and this 0 picosecond signifies the rise time and fall time. So suppose you want to create a pulse with some rise time, so you can change 0 to something else. And then this 5 nanosecond specifies the pulse width, the duration for which pulse has to be 1. And then this 10 nanoseconds signifies the total time period of the pulse. So playing with these two numbers, you can change the duty cycle of the pulse. So that is how we specify the stimulus to perform this our simulations on ELDO. Then we need to probe the different values. So the waveforms that we want to see, we need to probe it. So you can see that I am probing V and then star inside it. So star anywhere signifies that you need to probe everything that you can. So it will probe for all the voltage levels and all the current levels. So this was all about probing, and then we can perform different calculations also in on the eldo using this measure command. So you can see that first, to calculate the rise delay, uh, so rise delay means uh, the delay between 50% of input to 50% of output when output is rising. So for the CMOS inverter, when output will be rising, the input will be falling. So and the 50% for 50%, we are considering the value of output as supply by 2. So to to measure the rise delay, we use dot measure command, and then we need to give the trigger. Trigger is the time where the calculation has to begin, and then target. Target is the time where the calculation has to end. So since to measure the rise time, we have to calculate from 50% of the input. So we are giving input here, and supply by 2 is 50%, and it has to be given to measure the rise time, we have to calculate till 50% of the output. So here you can see that we are calculating for the till the 50% of the output. To calculate fall delay, the output needs to fall here. Here the output was rising. The only change that we need to make here, the output has to fall here, and since output is falling at this stage, the input will be rising. So you can see that I have made the corresponding changes to calculate the fall delay. TPHL is propagation delay from high to low, which is same as fall delay. Similarly, we can calculate the rise time and fall time of output. So we can define rise time is of the output as time taken for the output to rise from 20% to 80%. Uh, and so you can see that to calculate the rise time, we are calculating it at the first rising edge, and trigger is the value of the output when it is rising from 20%, and target is the value of output when it is when it has risen to 80%, and between the time we have got the rise time. Similarly, fall time is the time when output falls from 80% to 20%, and you can see that we are calculating the same on the output. So this was all about the calculation of propagation delay, rise and fall propagation delay, as well as rise and fall time of the output. We can also calculate the average propagation delay by taking the average of this TPLH and TPHL. And finally, since we are performing the transient simulation, we use this dot TRAN command to specify that we are performing the transient simulation, and this 1 picosecond specifies the resolution of the waveform to be plotted. So basically the tool will calculate output every 1 picosecond, and this process will continue the time t end. So t end, you can see that we have made the parameter t end as 100 nanosecond, and so the whole simulation is going to run for 100 nanosecond. So this is all about the basics of CIR file. So we have done nothing different. We have just included the gate level netlist, and then we have specified the PVTs, and then we have specified the stimuli, and then we are probing it or calculating different values, just like we did in the ADEL. So to perform the ELDO simulation, you need to go inside the inverter directory that you have created, where you have both the CIR file and the netlist file. You need to open the terminal here, and from here you need to convert first this bash cell into the C cell, followed by sourcing the path to uh, uh, the this file source slash mentor 2020 slash ams.cshrc. So uh, this will provide the path to invoke the eldo tool, and then you need to source the CIR file. So you need to press eldo followed by the name of your CIR file. So in my case the name was eldo in inv.cir. Further, you can press enter, and you can see that Eldo has finished with the calculation. So you can see that it is calculating propagation delay low to high, which is same as rise propagation delay or rise delay, and fall delay as this number. Similarly, you can see that rise time and fall time has been calculated. Further, to see the waveforms, you need to when you run this CIR file, you can see that .wdb file has been created inside the inverter, and we will be invoking the EZ wave tool, and we will be giving this .wdb file that has been created to this EZ wave tool to just get the waveform out of it. So you need to press here, and for transient simulation, to see the waveform, you can press on input, double click on output, and here you can see that when input is rising, the output is falling, just like the characteristic of CMOS inverter. Further, you can see that the rise time is calculated, the rise time of output has been calculated at the first rising edge. So this is the first rising edge, this is the first falling edge, this is the second falling edge, And similarly, this is the first rising edge of the output, this is the second rising edge of the output. And to calculate the propagation delay, so suppose we are calculating the rise propagation delay, you can see that we are calculating it at a first rise of output, and here the input was falling. So for the distance, this 50% of input to this distance, 50% of output when it is rising is termed as rise delay. So this was all about plotting the transient simulations on ELDO. Further, if you will see that uh, the rise delay and fall delay of the transistors are not equal. You will see that the rise delay is a bit larger number and a fall delay is a small number. It signifies that the rising time is very high, which means that the CMOS inverter, in case of CMOS inverter, our PMOS is weak because it is charging the output very slowly. And so we are getting a high rise time. So to play with these numbers, suppose it is asked that uh, we need to have equal rise and fall time. So here, looking at the simulation, you can see that this rise number is a bit larger, and so to make this rise number smaller, or rising time of output smaller, you need to perform the charging operation a bit faster, and for that you need to make the PMOS stronger, and for that you need to increase the aspect ratio of PMOS. So to do these things, you again need to go to the netlist that you have created, and inside the netlist you can see the instantiation of transistors. So this is the transistor PSVTLP and this is the transistor NSVTLP. So inside the netlist, you can play with these numbers W and L to obtain the parameters which you want. So suppose we want to make the PMOS a bit faster. So that for that we will be increasing the size of PMOS. So you can see that now I am doubling the size of PMOS. Earlier it was 0.135 and now I have doubled it to 0.270. Now, if we perform the ELDO simulation with the changed numbers, so now you can see that uh, this rise time and fall time have almost become equal. So you can so to have equal rise and fall time, generally we need to have PMOS double the size of NMOS. So in that way we can have equal rise and fall time. Similarly, we can model the different width and length values inside the netlist to obtain these parameters accordingly. One important point to note is inside the CIR file that we have written, uh, we have taken, since we are beginning with the simulations, it was just a tutorial video. We have taken these PVT values uh, to anything that we want, these process values and these uh, temperature and supply voltages. In case of PVT, P stand for this process, V stand for voltage, which is supply, and T stand for temperature. So we have modeled using anything we want, but generally in actual scenario, we always simulate for the worst case criteria. So suppose we are measuring these delay numbers and basically we are modeling the propagation delay number. So for delay, uh, uh, for the worst case condition, we need to have the PMOS and NMOS both as slow. So to model it, we need to use slow criteria, and then the supply. For supply, we need to keep supply as low as possible. So at low supply, we generally have a higher delay number, and then we need to have the high temperature value. So this is how we select the PVT. To benchmark any particular parameter, we need to benchmark it at the worst case criteria. So that is how we perform the ELDO simulation, which is useful in calculating various parameters that we have calculated. Similarly, in the DVD course, we will be calculating static and dynamic power using the CIR file. So after we are done with the pre-layout simulations on ELDO, we will be moving to draw the layout of this CMOS inverter. So for that, you need to go to launch and then launch layout Excel. So here you need to keep it as create new and configuration as automatic. Click on OK. Select the library, select the cell, and keep the type for inverter, and then press OK. So click on session. So you'll see that layout canvas will be opening. So this is here where we will be drawing the layout of this schematic. So so here in the layout window, first you need to make some adjustments. Like for that you need to press E button on keyboard. So that will open this display options menu, and here you need to change these resolutions of uh, these minor and major spacing as well as X and Y snap spacing, so that you don't face any issues while uh, drawing the layout. So I'll be changing all these values to 0.005 and then press on apply and then press on OK. So after you are done with this step, uh, what you need to do is, suppose I want to create an instance for say PMOS or NMOS. So you can press I button on your keyboard or choose instance from here, and then as we did in the schematic, uh, you need to go to CMOS 65 library and then choose an instance for PSVTLP or NSVTLP as we did there, and here you need to select the layout view. You can press close. uh, so you will see that an instance of PSVTLP will be hovering with your mouse. uh, you can place it and then press escape button on the keyboard. Similarly, to make an instance of NSVTLP, you just need to change this cell to NSVTLP, and then press hide, and then uh, I'll put it here. And now if I want to look into these layouts, you need to press shift plus F button on keyboard. So now I think that you will be able to see the layers, different layers and source and drain and gate region for these PMOS and NMOSs. So one important thing is to look into the layers. You can look here into the layers menu, and suppose I want to look about poly. So you can start writing poly, and you will see that for PO the color is red. So the red part here and here indicates the poly region. Similarly, if I try to write M1, which is metal 1, you will see that blue color with blue color regions are metal 1, and so these blue color regions, these represent metal 1. Similarly, you can do it for all the layers. So to start with all the layers, uh, what I want to say is the black region, the whole black region that you are seeing on the screen is your P substrate. And to make any N-channel MOSFET, NMOS, we make generally NMOS inside the P P-type substrate. So you, and for making the PMOS inside the p-type substrate, we first need to create an n-well, which is a region of n-type substrate, and then there we dope p plus source and drain to create a pmos. So for nmos, I don't need any p-well as such, because the whole black region is itself p-type substrate. So you can see that for if you closely see the structure of NMOS, you will see that this the red region represents poly, this blue region represents the metal connections, and this green regions represent the diffusion. This is where source and drain will be present. Uh, And if you will see the PMOS, these things are common in PMOS also. So you will see the red gate poly, and then you will see the uh, uh, green diffusion, the blue metals, and then also you can see there is a contact. So this contact will be used for making the connections. The thing that differ between NMOS and PMOS is here you will see that this layer is yellow in color and this layer is purple in color. So what happens is this diffusion is the reason of high doping. But to know what what doping it has been done to this diffusion, we need to consider that which layer is placed above it. So yellow layer, if I type NP here, you will see that yellow layer is present with this NP. So NP represent that my diffusion is highly N plus doped. Similarly, if you write PP here, mm, you will see the purple region here. So PP represents a highly doped P plus diffusion. So for making a P channel MOSFET, we need to create a highly doped P plus region inside the anvil, and so we are taking PP layer here, and here we are taking an NP layer here. One additional thing you will see in this uh, PMOS, which you will not see in NMOS, is this orange rectangle. So this orange rectangle is just the anvil. So if you will write NW here, you will see that this is shown by orange color. So since the whole black region represents the p-type substrate, and we are making a PMOS in this p-type substrate, we need to first create an anvil to make our PMOS. So here you can see that with orange region, we are creating an anvil, and then we are doping it accordingly. So for PMOS, we are doping it for with PP, and for NMOS, we are doping with NP, and that is how we generate the NMOS and PMOS. So I created this instance just because I wanted to give a bit of description. But to begin with layout, what you can do is you need to create here, click here, generate all from source, and then you can press OK. So you will see that some PMOS and NMOS has been created, and if you will zoom it, you'll see that some poly pins have been created. So for now on, we will be selecting all the pins and deleting it. And then uh, I can just decrease the spacing between PMOS and NMOSes as much as I want. So if I now try to make the connections, so you will see that the gate of PMOS and NMOS has been connected, as well as drain of PMOS and NMOS has been connected in the schematic. So I need to do the same for in the layout also. So you'll see that the gate is made of poly for both NMOS and PMOS. So I need to connect both of them with the poly only. So for to make the connection, you need to go and select PO here, and from here you need to select PO drawing, that is poly drawing. And then since we are interested in creating a rectangle, press R button on keyboard. So a rectangle like structure will start hovering with your mouse, and now you need to carefully go and create a rectangle here. So and with this poly, I'll try to connect the gates of both NMOS and PMOS. So now you can see that the gate connection has been made. Now I need to connect the drain of both also, and you can see that we have metal one connections over the diffusion of the drain. So we need to make the connections with metal one. So I'll selecting metal one drawing, and then again press R button on the keyboard to draw that. So let me make the connections for drain. So this is how I have made the drain connections. Now if I go to the schematic, you'll see that the source of PMOS is connected to VDD and source of NMOS is connected to ground. So for making that, for doing those connections, we need to create via. So uh, and so for ground, you need to go to create and then create via option, and then here you need to select P tap for ground. So and then we can press the hide option, and so I need to connect this source to this to to this P tab. So I'll vertically move along, and then maybe I'll keep this here P tab, and now I want to extend the metal one from here to make the connections here. So again we will go to metal one drawing, press R button here, and then start making this metal one connections from the source of NMOS to source of to this P tap metal, this metal one of P tap. So this is how we connect the we will be making the P tap for connecting the ground. Similarly, to make connections uh, with VDD to the source of PMOS, we need to create another via here, and here we need to create M1 NWL. So this is M1 NW. Uh, we can press on hide. So again, we need to extend it from here, and now we will be connecting the uh, source of PMOS by again selecting M1 layer and then pressing R button on the keyboard and then creating the metal one. So that is all about making uh, these connections, and now I also want to place the input, and this input needs to be connected to this ground, uh, but the pin that I'll be creating has to be a metal pin. So for that we need to move from this poly layer to metal one layer, and to move from one layer to another we need to create a via there. So again we will go to create and we need to create the via between poly and metal one. So here we need to select M1 PO, that is M1 poly. Uh, and then we can rotate this via for a better connection. So you can press here rotate and then hide, and then we need to place it over poly. So this is how we have tried to make the connections for our CMOS inverter, and now we need to make particular pins. So for that you go to M1 pin option, and then to create a pin we go to create and then go to create a pin. So firstly we will creating the input pin IN, and then uh, we need to click here at the input, and we can go at the option and change this height to, let's say, 0.001. This is just about changing the height of the label. So and then we can press on hide, and then we need to place input pins over this metal that we have created. So you can just need the pin and place the label here. So you'll see that this input pin has been created. The same I need to do for all the other pins. So we need to go to create pin, and then suppose I need to create the output pin. So I'll change the IO type as out and then press hide, and then draw the rectangle here and then put the label to create the output pin. Similarly, I need to create the input pin for VDD. So I'll Just type VDD and take it as input, press hide. And finally, we need to create the ground pin. So for that, again, we need to go to create pin, press ground, and here we need to select for input output, and then we can move to making the ground. So this is how we have made almost most of the connections, and we are done with connecting the pins there. So now we can save the layout from here. And to so the one of the major rule is the our layout must be DRC clean. So to check for DRC, we need to go to calibrate and then run nmdrc from here. So you need to run dkdrc, and here we have given the path of our DRC file. You need to give your username here and then press on OK, and then press on run DRC and overwrite option. So there are many DRC rules associated with the layout that we are making. So you need to have to go to filter and then select show unresolved here. And when you do this, you will see that these are all DRC errors. So there are 24 DRC errors in our layout, and we need to get rid of these DRC layers to finally make our layout DRC clean. So to get rid of these DRC errors, you just need to move the window a bit down, and then you need to click on a particular DRC error, and first select from here and then click for here and then press this sun button. So when you will do this, uh, some portion of the layout where there will be an error will start being highlighted, and you can look into this message which says what DRC error is present. So it says that rule OD area should be 0.054. So OD refers to the diffusion. So it says that this green diffusion has to have at least the area equal to 0.054, but in our layout the area requirements are not being fulfilled. So we need to go and increase the area of this green diffusion. Similarly, we need to check for all, keep on checking for all these DRC errors. So suppose this says that the width of this anvil has to be at least 0.4470. So this anvil that we have created is having a smaller width, and it is not fulfilling our DRC violation. So to learn how we are going to get rid of DRC violation, you need to go to every DRC, look into the message and look and do that particular correction, and then again run this DRC tool and this do this iterative process, and that is how you learn how to get rid of DRC. For now on, since I am already aware about most of the DRC, I'll be uh, removing those DRC error. So first thing was to increase the area of this n plus diffusion. So for that we need to flatten this p tab that we have created so that we can change or adjust different layers. So I'll go to flatten option and then press OK. So now I can now you need to change this full select option to partial select, so that now we are able to uh, adjust the layers height and width. So I'll just increase the this pp, and then since I wanted to increase the area, so one thing is you can do DRD notify on off is here, you can make it on. So if you make it on, all the DRC will start showing up here. So now you can see that it is saying that minimum area has to be 0.4, and till the point this DRC is being shown up, I'll be keeping on increasing this area. So here you can see that it has stopped showing me that, and so this is how uh, I I create the increase the area for our diffusion. Now, if I'll check and save and again go to this calibrate, so earlier you can see that there were 24 DRC errors. Now, if I go and run DRC again and overwrite it, now you'll see that some of the DRC error has been removed just because we have. So you will see only 20 results now. So there are only 20 DRCs now. 4 has been eliminated by increasing the area. So the next step is again go to the second one and then look into this. So it says the area of OD should be 0.054. So again this OD, this the same that we have done for PTAP, the same we need to do for NTAP. This M1 NVEL also, the diffusion of M1 NVEL. So for now on, I will not looking for all the DRCs. I'll just try to remove all the DRC errors with my prior experience. So uh, I'll have to again flatten it. Go to hierarchy and flatten. And since I need to connect the all the anvils, so I'll be just making sure that these two anvils are connected to one another. And then I also need to satisfy this minimum area constraint of anvil. So uh, I'll keep on increasing the anvil area, and I can also increase it on the top. So I'll keep on increasing it unless it shows me that the area 0.065064 has been satisfied or not. So now you can see that it is not giving me this minimum area 0.064. And now I'll keep it. I need to increase the size of area of this diffusion. So minimum area has to be 0.054. I need to cover it with NP layer. So you can see that I have made these connections. So another important DRC is this metal one area. So this metal one area has to be at least greater than a particular number. So I need to flatten it to ch change this area of metal one. So the minimum area has to be 0.042, and I'll be increasing the area till it shows me the flag 0.042. So once it has gone, it means that I have satisfied this minimum area of metal one, and I can keep it this here. So while you will do all these steps and save and check the DRC again, you will see that DRC has decreased. Another important DRC is, since the poly connectivity is very poor, we need to increase the connectivity of poly, and for that, this poly always needs to be covered with either PP layer or NP layer. So you can use anyone either of PP or NP. I am using NP for now on to cover this poly. So for that you need to create rectangle by pressing R button on the keyboard, and then okay. So first you need to choose NP drawing here, and then you need to create the rectangle here which covers the our poly. And so this is how you cover the poly. And uh, I think that uh, we are done with most of this DRC thing, and we can save our design. And now we can look into the DRCs. Go to calibrate, go to run DRC. So now you can see that earlier we have 24 DRCs. Now we are left with only 3 results. You can just go into it and see what are those DRCs. So you can see this NVEL has extended. So what I can do is I can just decrease this here, and to get this minimum area constraint thing, I can increase this area from here. So I think, and now if I try to check and save and then run DRC again, and now you will see that we are left with only one DRC, which is uh, about the edge length that we need to satisfy. So if I try to zoom over this DRC, so we need to satisfy for the certain edge length, and for that, so this final DRC error says that this anvil edge has to be at least greater than zero point 0.8. So if we press K button and measure it with the ruler, you will see that this anvil is 0.735, and so this edge needs to be increased from 0.735 to a bit larger number. Let's say so such that it is at least zero point 0.8, and then we will increasing the this anvil also. So then you can just coincide the anvil pin over it. Make sure that all these anvil layers are coinciding with one another. You can press on save option, and then we can again move to run DRC. And now you can see that no results found. So this means that all the DRC error has been resolved. So we have fixed all the DRC errors, uh, and we can say that our layout is DRC clean. So next we need to move to check the LVS. So for that, so move on to the LVS once you are done with the uh, uh, DRC clean layout. We will be again going to calibrate, go to run NM LVS, and here you need to again give your username, set your username in the rule set file, and then press OK. Uh, and then here you will see that home directory is not set. You need to set the home directory. So for that you need to change the username here. So I am giving my username. You should give yours username, and you will see that once you give the correct username, the whole thing, the whole path turns from red to blue. And then you can go to run LVS, override. So it will do the different checks for the layout as well as schematic, the pin check, sport check, and if all these matches, you will see this tick symbol and this correct written here. This means that the layout and schematic are functionally equivalent, and so the LVS has passed. So this is all about the layout. So once we are done with DRC and LVS clean layout, we can move to do the post layout simulations after doing picks from here and then carry on the next step. So that's all about the schematic simulations and layout of CMOS inverter.